Stone for time. Yeah.
You can go.
Final presentation in the ADA Dev Room for today. We're pleased to have Yannick Moy, is that correct?
Yep.
Moy, of ADA Core, who will present some new evolution in how to work with pointers in Spark, pointers that were long not included in Spark, but there's a lot of progress being made.
Yes. So I hope you'll agree with me that there's no best way to end up such a long day than with pointer analysis. At least I'm very excited by this project. When I joined ADA Core 10 years ago to start working on Spark, I had previously been working on analysis of C++, C. At ADA Core, I've also worked on analysis of Ada. And in all these languages, pointers end up being a nightmare. Finally, with Spark, we had a language which could be analyzed. But it was always like this small stone in your shoe that you cannot use pointers in Spark. And so we always had a look for that. And since the last 2 years, we've been working in adding some support for pointers in Spark, and I'm going to dig into that. So what is Spark first? It's a subset of Ada, but it's not like other subsets, just a coding standard. So it's a subset that provides you guarantees when you use the associated tools, so the formal analysis tools that come with Spark, which we call GNAT-proof. And you can go up to the full functional correctness of usually small parts of the code from something much simpler to achieve, which is a semantic coding standard giving you good guarantees about the code, like no side effects in functions, no use of pointers precisely. And if you go up between these two, you have here what we call the bronze level, which provides you guarantees about initialization of the data that you read and correct data flows and no aliasing. At silver level, that's about absence of runtime errors. So that's a big deal. That's where you've got the buffer overflow, integer overflows, all these kind of overflows and other runtime errors that are at risk for safety and security. And at gold, it's where you start really proving properties. So when you use your contracts, not only for dynamic verification, but you start proving in type invariance programming contracts. So the more you go up, the harder it is for the tool and for the user. But hopefully, the tool helps you go up this scale. So why didn't we use pointers until now? Because that's the view of pointers for Spark. That's the view, in fact, of pointers for analysis. If you want to do sound analysis where you don't miss any errors. That's the view of the complexity of using pointers, because yeah, you can end up with this mesh, but also of all the traps that pointers lead to. So in Ada, that's as full pointer support, you can end up with double free, you can end up with memory leaks, you can end up with pointers that point to deallocated memory. And there are a number of concepts in Ada, features that help you avoid these problems, but still with unchecked deallocation. So the Ada name for free, you have all of these. So there are uses for pointers in Spark. In particular, when you have some data structures that need pointers because they need to grow, for example. So that's typical for containers that don't have a fixed size. Because they have elements that don't have a defined compile size. So for example, strings or any indefinite type in Ada that you must point to. That's the same for class-wide types, so the objects in Ada that were mentioned before. Or because you have a recursive data type. So if you want to have your own list or tree or similar recursive data type, you need to use pointers. So what changes with ownership? So this concept that has been used in other languages, the most famous being Rust. What changes with ownership is that it brings these great crew solutions, so concurrent read exclusive writes, which is exactly what you need to analyze code. So that's what already we're using in Spark for analyzing code with references. So references are these special pointers, if you like, so pointers at the executable level, but not at the source code level, that can be manipulated when you pass arguments to a function in-out, input or output. And in that case, that's Spark already analyzes the calls to make sure that there's no conflicting aliasing between things through which you will write. So there will be only one writer in the function. And if there's one writer, there won't be any reader through another path. So we already do that in Spark for references. So of course, for pointers, we want to do the same kind of non-aliasing check with some addition, because if you have pointers, you can assign pointers all over the place. So you can create your own local aliases. And this is the kind of thing we want to prevent, and that's where ownership kicks in. So when you are going to assign a pointer to another object, you're going to move the ownership. And if you stop that, you can do useful things, but you're still stuck. For example, if you want to traverse a recursive data structure without destroying it, because each time you're going to move your current pointer, you're going to destroy it, you're going to take the ownership of the things you had before. So what you need for that, you need some local handles that will restore the ownership when the scope is finished. So where we observe the data that maps to the Rust concept of mutable borrows or simple borrows. So what's provable with this pointer ownership? So we have a prototype right now, and what you can do is you can write this kind of code with a pointer type that is an excess. So that's the way to denote in Ada pointer to T. And you can implement these swap contents or swap pointers. And so I don't show the code of the body, but you can imagine very easily swap contents will swap what's underneath these two pointers by differencing them and using a temporary variable. And swap pointers will simply swap the actual values of x and y. That's why swap contents takes just input parameters, x and y, and swap pointers takes in-out, because it will change the value of these objects. And so if you put the right precondition, postcondition here, not only you can prove with the Spark tool, you can prove that all of these references, so in Ada it's .all to the reference an object, are safe, so the pointer is not null. And you can prove what you usually prove with Spark, absence of runtime errors in general, and contract. So here that the postcondition holds. So they are essentially the same, except here you're repeating the non-nullity of the arguments. And all this because we can assume, thanks to the ownership system put in place, that when swap contents and swap pointers are called, their respective arguments are non-aliased. That's very important here, otherwise you cannot verify this implementation. So that's what it does now. Let's look now at every one of these operations that I mentioned, the move, borrow, and observe operations. So the move is when you assign a pointer. So that's either an assignment statement or when you're passing an out or in-out parameter in the procedure. And the thing that you're assigning from loses the ownership of the data and becomes unreadable. And the ownership goes to the thing you're assigning to. So for example, the implementation of swap pointers can be this one. I take a local variable temp here that takes the ownership from the value pointed to by x. Then I can write into x. So I cannot read x, but I can write into x the value of y. And then I can write in y the value of temp. That's correct. So now if I make a mistake, so for example here, instead of writing temp into y, I write y. Well, y was moved already here. So I cannot move it again. It was moved into x, so I cannot move it again. And our borrow checker, so our implementation of these rules in the compiler, say that there's no sufficient permission for doing that. The object was already moved. If we make another mistake now, so instead of moving temp, I'm moving x. So here, y was moving x, x was moving y. So that seems like not very useful, but at least for these two lines, that respects the ownership principles. But when you return from swap pointers here, it realizes, so that's why it's pointing here to the spec file, it realizes that there's not enough permission for x. So x, you're supposed to return to the caller with this parameter with full ownership of the underlying memory. There's an implicit assignment, and here it realizes that's not possible because it was moved here. Now let's listen to the borrow. So borrow occurs when you're passing an input parameter of access type or pointer, and temporarily the actual parameter, in the call will lose ownership of the thing it points to, and it will regain it automatically. So it's an input parameter. It doesn't change through the call, the actual value of the pointer. And there will be non-aliasing checks, like for references before, that there's no possible conflicting aliasing between the arguments. So for example, if I call this swap contents, so swap contents was taking input parameters, x and y are okay. There are two different pointers here. X and x is not, and it will be coded by the non-aliasing checks. Now let's look at the more complex borrow, the local borrow. So we can define a local variable here of an anonymous access type. That's how we distinguish this from the move. And here, because we're writing that, the ownership system understands that we are borrowing x into this local variable. What it means is that for the scope of the local variable, x becomes unwritable. And so here I can still write, but through the borrower to the underlying memory pointed to by x still, but that it doesn't own. So I can implement swap contents like that. Let's look at what happens if I make a mistake. So if here instead of local x, the borrower, I mentioned the borrowee, I get an error that says that the object was already borrowed before. And that's all for borrows. Finally, last operation, the observe. So the borrow here was the mutable borrow of Rust. The observe is just the regular borrow. That's for passing parameters of composite type, so an array, a record, or combination thereof that has pointers in them. Here we're going to consider that the parameter only provides a read-only view to all the memory underneath, all the possible tree of data. And that's the same for defining a constant of this type. Again, the top-level object in Ada is immutable, but in Spark, for this ownership system, we're going to consider that all the tree of pointed to data is also immutable. That allows formal analysis. And after the scope of the call or the scope of these constants ends, then the original object recovers its ownership. During this scope, both objects, the borrowee and the borrower, have a read-only permission. So let's look at an example. So this was for constant and parameter. The more complex observer is like previously, the local observer. And here we recognize it, that's our choice of design, by saying that it's local variable of an anonymous access to constant. So not a name type like before. And here, instead of a move, again, we do an observe. So y has a read-only access to the underlying memory, and during its scope, y also has a read-only access. So I can read local y here, and the memory pointed to, and I could replace this local y by y. So that works. When I make a mistake, so if I move the final assignment up inside the scope, so here in the scope where y is observed, it's an error to try to write through y. It's a read-only access to the underlying memory, and that's what the board checker says. So there are some limitations. We are only focusing right now on what we call in Ada pool-specific types. So not the general access type that's when you define the access type as all or constant, because these are much more liberal in Ada, and that would be much more complex to define the rules for having proper support in Spark. So it will be either limited, or there won't be any possibility to take the address of a variable in the stack. So that's the kind of things we're discussing right now to define the exact rules of what we want to allow and what we can implement in the checker. In any case, it will be less powerful than the system of Rust. We don't plan to have any annotation, in fact. We want to have something that integrates very well with existing code or code that is regular Ada, even if it's new. And so we don't plan to have annotations for lifetime. We want the borrowing-observing relationship to be statically known. Some of these constraints come from the wish to have no additional annotations, and some other come from the fact that we want to do the goal is different than from Rust. We want to be able to do formal verification. And so, for example, this statically known relationship is something very important. Otherwise, you end up with things that are much more complex like what researchers do exploring formal verification at first end up with. There are things that are specific to ADA. So when we adapted these ideas to ADA, there are different types. And for example, array types. When you take an element of the array, when you move it, you're going to mentally move all the array because you don't know which cell it is. So if you want to, for example, swap elements in an array, you will have to do it through a call, so that the call hides the fact that two different elements of the array are moved. You won't be able to do it just taking index I in a variable and then doing the swap locally. So there are some kind of limitations that come from the limitation of the static analysis. In terms of roadmap, so what we expect to do by the end of this spring, so May, June, when we issue the GNAT community release, which now includes Spark and GPS and everything. We hope to stabilize the reference manual rules. So we're still working on this. So if you want to have a look, if you're curious, that's there, that's online. And yeah, it's still a bit evolving to make sure that we have something sound that maps to the implementation. To complete the implementation of the ownership checking, so what I showed was what's working right now, but there's still a lot of work to make it work in all conditions and to implement all the rules that are already defined. And to adapt the flow analysis engine. So Spark goes in two different stages for analysis. There's this flow analysis that does local static analysis, simple one for all the flows, reaching essentially the bronze level. And then there's proof, where we use provers under the hood and to reach the higher levels of guarantees, so silver, etc. So we want to finish that flow analysis, which we haven't started. And for the next years, we want to support local borrow and observe in proof, which we don't do right now, so it's more complex. To support proof over recursive data structures, and here what you want to be able to do is to quantify over the content of these things. So for all elements of my list, I have this property. So that's more complex. We have prototypes in the underlying technology Y3, and we have to lift that to Spark. And to check absence of memory leaks. So the rules are set up so that we can check that by proof, and we haven't done that yet. And I think that's all. Thank you. Yes?
First, I really like this whole project.
Okay. I think it's cool too.
So my question is about, at the beginning of the talk, you talked about use cases.
Yeah.
And one use case was, for example, this container where you don't know how much content will be in the container.
Yeah.
And now you are, at the end of the talk, you point out a few limitations.
Yep.
So I wonder, can you circle back to the use cases
Yep.
and explain, for example, is it possible to create an AVL tree or something like that? And now with this new technique now?
So so it's planned, but the proof support right now doesn't support recursive types yet. It will. So the three use cases that I mentioned, it will. The first ones, the first two ones are the easy ones that are supported already. Well, partially because flow analysis is not there yet, etc. But just having a tree which is not recursive, yes, is already supported. Yeah, so that's cool. Welcome. Yes?
The analysis that you're doing local to the function, or do you need to deal with the whole problem?
Yeah, so Spark works locally. So in order to be able to do this powerful analysis using SMT solvers, you have to be modular. Otherwise, do something else like symbolic execution that traverses the thing and bounded symbolic execution. So we are in the realm of deductive verification, where we really are looking at a piece of code. Although we do things like inlining, so there are ways to go around these limitations.
So I saw that one of the rules is that a single pointer is not borrowed twice, right? Doesn't appear twice in a call.
Yeah.
To the call, right?
Yeah.
And what happens if the pointer is a field in an object
Yeah.
that was received by the function?
So that's the same. So I mean, what I just used examples that use a plain variable, but the same applies to fields. I mean, fields are followed individually. So what we have in terms of implementation is that we unfold on demand the structure of the tree of the type to go deep inside the fields of a given variable. So you can borrow, for example, if you have something that points to